Okay, time for another physics video presentation. And today what we're going to talk about is torque and equilibrium. So we talk about a lot of motion that goes on in physics, but now we're talking about things that are in equilibrium. Standing still, we're continuing to do the same thing that they've been doing. So let's talk about it a little bit. Now we've talked about forces being in balance, but now with rotational motion we have to talk about torque being in balance as well. So the first thing that we have to talk about here, the first rule of equilibrium, is don't talk about equilibrium. No, wait, that's something different. The first condition for equilibrium is that all the forces are going to balance out to zero. And that means that the forces in the x direction have to balance out to zero, and the forces in the y direction have to balance out to zero. And we did this during our Newton's laws section, and now we're doing it again. But this time around, we are talking about torque as well. So the torque also has to add up to zero, otherwise there's going to be some kind of rotational motion going on and some kind of angular considerations. So the torque at zero and also the forces at zero is part of the stipulation here. Okay, so what you're going to do now is you're going to be picking where the point of rotation would be. And I'm going to point out from the beginning here that you could pick a point of rotation that was anywhere on the object, but it's usually good to pick one where we're at the torque equaling zero, and that would mean if we pick a rotation where there's one or more forces acting, then since the radius from that point would be zero, we eliminate some of our values there for torque. I'll explain that in a couple of example problems that we're going to be doing in a little bit. Okay, and here's an example problem right now. So we have a woman sitting over here, and we have a man sitting over here, and this actually looks more like a child, doesn't it? But at any rate, they would be of different masses, but they want to be balanced out on this plank here. When I was a kid, we used to call this a seesaw. I don't know if they have those anymore, seesaws. They can be dangerous. But at any rate, here is a picture of that, and what we're going to try to do is find the distance x, that's this distance here, that the heavier person would have to be at in order to balance things out, so they could both be balanced on the plank here, the plank that we used to call a seesaw. All right, so we're going to look for the normal force. Here's the normal force pushing up. And we're also going to look for the distance away for the heavier person. The heavier person has a weight pushing down. There is also the weight of the plank that we have to talk about pushing down. And here is the weight of the smaller person here. All right, let's go through this problem. Here's a bigger picture to talk about what I was saying there. Here again is the normal force pushing up. We're going to look at the distance here where this person would have to be. Here is the weight of the plank pushing down, the weight of the heavier person, and the weight of the lighter person. Let's talk about first the second condition that I mentioned there, and that is that the sum of the torques have to be equal to zero. So I'm going to go back a slide, but I'm going to pick, and it should make some sense, this point as my point of rotation, my axis of rotation. I could pick any point I want. This one is a good one to pick because it's where two of my forces, the normal force and the weight, the force of gravity of the plank, are acting. So that means my torque will be zero because their distance from this point will be zero, and that means their R will be zero. And that's why here I'm saying here's the torque of the normal force, here's the torque of gravity for the plank, and here is the torque for the man, and here's the torque for the woman. And since torque is force multiplied by radius, I could say that there is zero torque for the normal force and zero force for the force of gravity of the plank. They're located right here at the point of axis, no radius, no torque. The man, I'm going to say, has a torque of negative capital mg multiplied by x. I'm going to go back a slide to explain that. The torque here is the force. Well, the force here is the force of gravity, so there's the capital mg. And the radius from the point that I picked is x, as you can see. Why negative? Well, if you remember from previous videos, this force would have the man and the plank rotating clockwise. And clockwise is a negative torque. That's the convention. So, here we go. There's my negative mgx for the torque of the man. Here's my torque for the woman. It's the smaller letter m multiplied by g. That's the force multiplying by her radius, which we know to be 2 from the point that I picked as my rotational point. Let me go back again and show you what I mean. The woman over here has a force, mg, pulling down, which would have the plank going counterclockwise, and her distance is 2 meters. So that's the force multiplied by the radius, which we now know as torque. So there is her value, mg2. All these things have to add up to 0, so I can say that mg2 is equal to capital mgx. I can get rid of the g's, and here is my value for x. I hope that made sense to you. And of course, if it didn't make sense to you, bring that question with you back to class. We can talk about it there. Let's talk more about this idea of equilibrium. Because we also wanted to find the normal force. So here are the sum of the forces. The force of the man would be negative. That's the weight of the man, capital M.
Taylor, please come to the main office. Sean Taylor.
How about that? All right. That wasn't really meant to be part of the presentation, but there it is. All right, so the forces. There is the force of the man going downward. That's his weight. There is the force of the woman going downwards. We use that as a negative. There's her weight. There is the force of the plank going downward. That's the weight of the plank. So the mass of the plank multiplied by g, the acceleration due to gravity, plus the normal force, which is the only force going up, and all those will equal to 0. So let me point that out again by going back to the picture, and we could see the normal force going up has to be balanced out with the weight of the girl, the woman, the weight of the plank, and the weight of the man here, I guess, right? Capital Mg. So that's my explanation there. There's no forces in the x direction to think about, right? There's no force at all going in either one of the horizontal directions. So I don't have to worry about those for this particular problem. And there again is my solution for the normal force. Okay, hopefully that makes some sense to you. And if not, bring your questions with you back to class. We can talk about it there. And we'll go on with our discussion of equilibrium. Okay, we have already talked about the center of gravity or the center of mass. For our purposes, they'll be the same thing here. But yeah, when we're looking at objects, sometimes we have to know where the center of the object is, the center of mass for the object is. And if it's a uniform object, it'll be right at the center of the object. Many of the problems do that. But if there's other things going on, we have to take this into consideration. And that's important. Okay, if you remember the center of mass or the center of gravity equations, we did it by multiplying, we added up all the masses multiplied by their radiuses, that's what I'm doing here, and divided it by the total mass. So that's what we did there for the center of mass. That's a little bit of a reminder for that. We'll be using that a little bit later. And as I said again, for an object that's uniform, the center of mass will be right in the center of the object. One more thing to point out here is that just because there is no net torque, it doesn't mean there's no motion or no rotational motion. Just like we did with Newton's laws, this could mean that the object is continuing to do exactly what it was doing before. And let's see here, I'm going to take a short break and we'll come back and talk about some more of these considerations in a moment. All right, and we're back at it here. Okay, so here's a couple of things for these equilibrium problems now that we're getting into them here. One thing is, like I said, pick where your rotation axis is going to be, and I would pick one where a couple of forces are, because that'll cut the torques out right away. Free body diagrams are good to show what's going on. And yeah, if you have more than one object, draw more than one free body diagram. Draw one for each one of the objects. Those are some tips for you. What else do I have for you here? All right, so apply the torque equation here. That one works out pretty well if you start with the torque, as I did with the seesaw or the plank problem, and then go with the first condition, which is the idea of the sum of the forces would be equal to each other. All right, and then you're going to just make the substitutions, and the more you practice these, the better you're going to get at them, of course. Okay, so just the idea of taking a look at the object that's going to be analyzed here. Here is a forearm. So they use these kind of things to talk about anatomy and physiology also, right? Okay, so let's get into some examples here. Here's a free body diagram. This is a classic problem for equilibrium. It's a ladder problem. You have all kinds of problems involving ladders. But here's just the ladder by itself, and it's at a 50-degree angle, and it's just getting ready to slide. So let me present the problem to you. I'm going to blow these pictures up for you a little bit. But here is a ladder, 10 meters long. You have it in your notes already. It's 50 newtons, so when they say smooth vertical wall, they're trying to tell you that there's no friction. And yeah, just about to slip at a 50-degree angle, and we're going to look for the coefficient of friction. All right, well, let's strategize here and see what we can do. Here is our picture of the ladder at its 50-degree angle, and what I've got going on here is the free body diagram. So there's the normal force pushing up. You can see that one. There's the force of friction that the ground is offering, pushing this way. There is, now here I'm putting the 50 newtons at the center of the ladder because it said it was a uniform ladder. So that means that the center is at the center of the ladder, and that's where we're going to put the weight of the ladder. A 50 Newton ladder, where would you put that? Would you split it into all these parts? No, this is where the center of mass part comes in. So the center of mass is at the halfway point. That's where I'm putting the weight of the ladder. P, for some reason, P is going to be used as the pushing force, I guess, of the wall, and that's going directly out here, the force of the wall. Let's see what we can do here. First of all, I'm doing the business with the sum of the forces. The sum of the forces here. This was the second condition, that the forces would balance out to 0. So in the x direction, the forces have to be 0. And that means that the friction, which they use the letter F for, hey, how about that? All right, the friction working in one direction minus the force of the wall is equal to 0. So with their terminology here, the friction minus the P force of the wall is equal to 0, and that means that friction and the force of the wall are equal to each other. Let me go back to the diagram to explain that a little bit better. The friction in the x direction going this way, I called that positive, minus the force of the wall, the P force over here, have got to be equal to 0. So that's why I did that. So I could see that these two things have to be equal to each other. They're the only forces in the x direction. Okay, similarly, the normal force going up in the y direction has got to be balanced out by the 50 newtons that is pushing down, if you can see that. Let me go back to the equation here. So the sum of the forces in the y direction is equal to 0, which means that that N force, that normal force pushing up, minus the 50 newtons going down, has got to be equal to 0, which now gives me the normal force is equal to 50 newtons. So I'm getting a little bit closer to finding this coefficient. I will need to talk about the torques here. And here we go. Okay, so the sum of the torques have to equal 0. So the torque of the friction plus the torque of the normal force plus the torque of gravity, the gravity that's acting on the ladder, plus the torque of the wall's force, every one of these forces potentially have torque, have got to add up to 0. Now you see here, the torque of friction and the torque of the normal force are 0. Let's see why. I'm going to go back to the equation. Well, I'm choosing my point of rotation to be right here at the bottom. If I pick it right here, I've got two forces that are going to cancel out in the torque equation immediately. All right, since I have a 50-degree angle over here, I can say that the wall's force is going to be at 50 degrees also, and the force over here is going to be at 40 degrees, right, from the ladder. So this is acting at 40 degrees here. So the radius is going to be this distance up here, and the force is 50. Remember, though, that for torque, it's the force multiplied by the radius, but also it's by the sine of the angle between them. So remember that, 40 degrees over here, 50 degrees over here. Let me go back to my calculations. All right, so the friction from the ground there is at a radius of 0 from the point I picked, so it cancels out. The normal force also at a radius of 0, so it cancels out. Gravity would have the ladder rotating, left to its own devices, rotating clockwise. Clockwise comes out to be a negative, so 50 is the force. The radius is 5. Remember, the ladder is 10 meters long, so the radius is right in the middle there at 5. And remember I said the angle between them was 40 degrees, so there's the sine of 40. So the torque of the wall is the force of the wall. I don't know its value yet. I'm about to, though. It's at 10 meters from the point that I picked as my point of rotation. It's on the other end of the ladder. And as I pointed out before, the sine of the angle between them is 50 degrees. So solving for P, I get the 21 newtons. P, remember, is equal to friction.
Mr. Rooney, can you call 6325? Mr. Rooney, 6325.
Hey, this is probably why I don't make videos in the at the end of the school day too often, because the announcements come in a lot. But we won't let that throw us off. After all, physics is fun. All right, back to the problem. So we know from the beginning that P, the wall's force, is equal to the friction. We also know from a while ago that friction is the normal force multiplied by the coefficient. We already figured out P. We figured out the normal force. We solve for the coefficient, and it comes out to 0.420. I hope that made sense. And of course, if it didn't, then bring your questions back to class, and we'll try to answer them there. All right, let's take a look at another one here. Here's a horizontal beam, uniform. That means the center of mass will be right at the 2.5 mark. It weighs 300 newtons. It's attached to a wall by a pin connection that allows the beam to rotate. Okay. All right, so let's see. Its far end is supported by a cable that makes an angle of 53 degrees with the horizontal. I have a figure for you. A person weighing 600 newtons is standing 1.5 meters from the wall. This is in your notes already, or your problem, PowerPoint problem paper that I gave you there. We're going to find the tension and the R force exerted by the wall and the beam. Well, I'm confused. I don't know about you, but let's take a look at a diagram. That's why drawing a diagram can help out. Here's the person, 600 newtons. They're standing out on the beam here. Here's the tension, and there is a pin that lets it rotate. All right, now, something that's different about a problem like this, it's going to be a variable tension, but this time we can't say that the wall is just supplying a force in the horizontal direction. It's going to supply a force that's also going to counteract the tension in the y direction, and I'll show you what I mean by that with my free body diagram. So what I'm saying here is that the R force is going to be at some kind of angle. I don't know what that angle is, but I can't say that that force there just pushes out horizontal. The tension I know is at 53 degrees, and there is, remember, it's a uniform board of 600 newtons, or 300 newtons rather, so my 300 newtons is right here in the middle of the beam, and here's the person's force, the 600 newtons going downward. So here in the next diagram, and I believe I blow this up for you, right? Here's that R force at some angle. I don't know exactly what it is. Here's the tension. Here's the force of the beam right in the middle. And here's the force of the person, the 600 newtons. Because this R force has two components, and because I balance out these forces in the X and the Y direction, I'm going to say here's R in the X direction. Here is R in the Y direction. I'm also here splitting the tension into its components. So I'm taking my free body diagram and breaking it down a little bit more. I'm putting the 300 newtons here right in the middle of my 5-meter beam at 2.5 meters. And here I'm putting the person where they're located at 1.5 meters. And there's their force, the 600 newtons. All right, now this is a little bit more of a complicated problem, but it follows the same steps. So why don't you give that problem a try, see what you can do. These are the answers that I have for the tension and that R force, the force that the wall is supplying. See how you did, right? This is a tough one. But I'm not going to show you the solution. You're going to try to come up with a solution, and we'll do that back in class together if you have any questions. And you very well might, but give it a shot. See what you can do. If you have success, then you're going to have a lot more confidence in these problems moving forward. And that is it for our presentation for today. So thank you for watching, and I look forward to seeing you back in class.